Right, so you might be thinking, why neural networks at a front-end conference? So firstly, I think it's really important to understand the hype. There's a lot of hype about neural networks at the moment. You hear it all over the place, and sometimes it can seem like they're going to solve all our problems. And if you don't understand how they work, that's quite a tempting thing to believe. So I'm hoping that this will give you a bit more of an understanding of that. There's also a good chance that you will have to interact with them at some point. If you're not already working on a system that uses them, there's a good chance that you will in the near future because they're getting more and more pervasive. And they're not actually as hard as you think. They sound very complicated, but hopefully you'll see after this talk that they're not as hard as you think. But they are pretty amazing, and I think it's always quite fun to come to a conference and hear things that are a bit outside your normal day job, and it might make you think of a new idea that you can incorporate into your own work. So this talk aims to give you an intuition of how neural networks work. I'm not going to try and explain all of the mathematical background, but you can always go away and read more about it if you want, and hopefully, having heard this talk, you will have a bit more of an understanding, and it'll make it a bit easier to get your head around the maths. Don't worry if you don't follow everything. I've tried to pack a lot in. It turns out it's quite hard to teach neural networks from scratch in 30 minutes. So yeah, don't worry if you don't follow everything. It will just give you a general gist. And we will make some simplifications, but hopefully it should all still be correct. And basically, this is the talk that I wish I'd seen when I started learning this stuff around 6 months ago. So as Phil has kindly introduced, I am a technologist with a background in computer science, physics, and philosophy, and it's been my doctoral studies that really got me into neural networks. And I also, as Phil said, recently founded this community group which aims to look at how technologies like AI will impact society in the future. So we're going to try and cover how neural networks differ from conventional computing, what is in a neuron, what is a neural network, how to train them. We're going to look at a specific type called convolutional neural networks, and then we'll look at some fun applications of them. But before we get going, I just want to ask, who feels pretty confident that they know what a neural network is and how it works? Oh, okay, quite a lot. You might be bored. I'm sorry about that. Who feels like they're interested, they've tried to read about it, but they got a bit confused and pretty much gave up? Okay, this is probably for you. So just a bit of history. They're not actually a new technology. They were first sort of researched in the 1940s when they were given the name cybernetics, which I actually think is a much cooler name, and I wish we stuck with that. But they were abandoned quite quickly due to some perceived logic limitations. For example, they couldn't model the XOR function in that state. Then in the 1980s, they had a bit of a resurgence, and at that point it was called connectionism. But again, they were abandoned quite quickly due to a lack of capable hardware and large data sets. Then in 2006, there was another resurgence, and this time it's normally called deep learning. And now we've got much better hardware. We've got like graphics cards and things that are optimized for machine learning. And we've also got the internet, which provides this really rich source of big data. So perhaps the time is right, and maybe they'll stick around. OK, so let's have a look at how we might want to write a program to recognize a cat in a kind of a conventional program. We'd probably have to chain together a whole load of if statements. So if the image is furry, and it has a tail, and it has 4 legs, and it has pointy ears, and so on. And you can probably imagine that that's going to get pretty long. And also, a lot of those qualities aren't unique to cats. So that could also correspond to a dog or a fox. And it also won't catch those weird edge cases like a tailless cat or a cat who only has 3 legs. But in this method, we're basically programming explicitly what features the computer should look for. With a neural network, however, you essentially give it a whole load of examples of cats and a whole load of examples of not cats, and the machine works out for itself what features to look for, what's important to kind of catism. So I think this is quite a useful diagram to kind of get your head around it. So on the left-hand side, we've got a straight line that tries to divide up the green dots from the red dots. So the reds represent cats and the greens represent dogs. And it's doing a pretty good job. It's getting them roughly on the right side, but there are still quite a lot of random anomalies that are on the wrong side of the line. But that's a really easy function to model in a normal programming language. Whereas on the right-hand side, we've got a really crazy, wiggly line that is a really complicated function that it would be pretty much impossible to try and write this out as an equation. But it does manage to catch all the weird edge cases. And it's actually that kind of complicated function that a neural network is able to learn. So they are biologically inspired. They're called neural networks because they were inspired by how our brains work. We're very good at kind of pattern matching and recognizing things from examples. And the machine is learning a complex multidimensional model, and that's what allows it to account for those weird edge cases. So my rule of thumb is neural networks are good at things that humans are good at, like pattern matching, and they're bad at things that computers are good at, like maths and logic. So you don't want to use them for everything, but you want to use them for things that are difficult for computers to do, but easy for humans to do. OK, so let's try and get our head around them with a trivial example. Imagine I'm trying to make a decision about whether I should go to a festival or not. So I might consider things like, will the weather be nice? What's the music like? Do I have anyone to go with? Can I afford it? Do I need to write my thesis? Will I like the food? All of those sorts of things. So just to take the first four for simplicity, I would think about all those factors, weather, music, company, money, and I'd probably think about how important those things are to me. Multiply up the inputs by their importance, sum that all up, and if it's over a certain threshold, I would go to the festival. And it's kind of just like weighing up the pros and cons, and we do it all the time without even realizing it. So let's put some numbers on that. Let's imagine the weather is looking pretty good, kind of sunny, but with a bit of cloud, so we'll give it a 3. But the weather is really, really important to me, so I'm going to give it a 4 for importance. The music, maybe the music is not my favorite, but I also don't hate it, so it gets a 2 out of 4. And again, it's not too important to me, so I'll just give it a 2 out of 4 again, and so on for the other factors. I then multiply those up. I sum up all the results. I get the answer 26. I check whether that's above my arbitrary threshold, which I've chosen as 25, and it is, so yes, I will go to the festival. So maybe you can remember from maths at school that if you have an equation, you can move things from one side of the equation to the other. So that's what we're going to do with this threshold here. Move it from that side to the other side. So instead of having plus 25 on one side, we now have a negative 25 on the other. And that just goes into the addition. And now instead of checking whether we're over 25, we check whether we're over 0. And that just makes things a bit simpler mathematically. So to generalize that, we have a load of inputs. We have a load of weights, which correspond to the importance. We have this random extra number called a bias, which has come from moving the threshold to the other side. And then we have what's called an activation function, which was our test about whether or not it's above a certain threshold. And then we have our output. And what's in that circle there is essentially one neuron. So to make a neural network, all you do is chain up loads and loads of neurons. So you have an input layer, and the outputs of the input layer flow through into a hidden layer, and then the outputs of that flow through into the output layer, and then that gives you your result. To make a deep neural network, all you have to do is add an extra hidden layer. Turns out that if you have 2 hidden layers, or more, 2 or more hidden layers, it can count as a deep neural network. OK, so far we've only seen a binary output. I was just wanting a yes or no answer to whether I should go to the festival. But what if you want an output that isn't binary? So this is where more complicated activations functions come in. So we've used this step function so far, so it's just a basic threshold. So below 0, it will give me a 0. Above 0, it will give me a 1. So you just read along the x-axis and find your value, and then see where it matches on the y-axis, and then that's your output. So the middle one is called the sigmoid function, and that was popular historically. And it's essentially a smoothed out version of that step function. And it just means that instead of having only a 0 or 1 answer, you can have a kind of more gradual, continuous curve of an answer. And then on the right-hand side, we've got the ReLU function, which stands for rectified linear unit. And that's what's most popular these days. And all that does is say, if it's below 0, my output is going to be 0. And if it's above 0, my output will equal my input. So those functions, those graphs go there in that diamond where the activation function was. OK, so we've had a bit of adding, subtracting, and a couple of graphs. So it sounds like it's all simple arithmetic then, right? Sadly not. The difficult bit is actually figuring out what all the weights and biases should be. So I just handpicked those numbers in the example of the festival because I knew what I wanted the output to be. But actually, when we train a neural network, we are asking the network to learn the values for the weights and biases. So the short version of training the network is you randomly initialize the network's weights and biases. Then you get a ton of labeled training data. And what I mean by that is a load of pictures of cats that have got a labeled cat, and a load of pictures of dogs or whatever else that have their appropriate label. For every piece of training data, you put it into the network, you let it go through all the neurons, and you see what result pops out the other side. And you say, did the network get it right? Did I put in a cat and did the network say cat? Or did I put in a cat and the network say dog? So if it got it wrong, how wrong was it? And then we nudge the values of all the weights a little bit to increase the probability of the network getting it right the next time. And then you repeat that over and over again with each piece of training data. OK, so let's just visualize this. We have our picture of a cat, and we have put it into the network. And then, unfortunately, we have an output of 62% probability dog and 38% probability cat. And obviously, we want it to know that it's 100% cat. So what we do is just go backwards through the network and nudge all of the weights a little bit to try and increase that probability. OK, so we're going to go into a little bit more detail about how we do that. And this can get a bit tricky, so don't worry if you don't quite follow it. Again, it's just about giving you a general idea, and hopefully, if you're interested, it'll make it easier to then read more about it. So how do we know how wrong the network is? We measure the difference between the network's output and the correct output using what's called the loss function. So the loss function is also helpfully called the error function, the energy function, or the cost function, depending on what paper you read. And it took me a long time to realize that they are all actually the same thing. So hopefully that will save you some time. And the best loss function will depend on the type of your data and also the intended application. But a simple example is mean squared error. So I don't know if you can remember maybe from school trying to fit a line to some data points, and you're trying to find the line of best fit. And you look at the distance between your data points and the line, and you basically try and minimize the distance between all the data points and the line. That's essentially what we're trying to do here. So they can get mathematically complicated, but all you need to do is think of it as the difference between what the network should output and what it does output. So the goal of training is to find values for the weights and biases that minimize the loss function. So I'll try and explain what that means a bit. So normally, with a neural network, you'll have loads and loads and loads and loads of neurons, and each neuron has its own weights and biases. So you're going to have like thousands of weights and biases. But for the purposes of this, because I find it hard to visualize in any more than 3 dimensions, we're going to pretend that we only have to find 2 weights. So in this diagram, we've got 2 axes that have the weights on, and then we have the vertical axis that has the loss. So when we randomly initialize our weights, we could end up anywhere on that graph. So let's say we end up at this, we start off at this starting point that's quite high up. And what we want to do is minimize the loss function. So we want to find the lowest value possible. And looking at that graph, we can all see that the lowest point is where I've marked it here on that kind of blue dip. The problem is that the network can't just look at the whole graph and know where to go. It can only see a kind of localized area, so it only knows what its current weights are. So we have to help it figure out what direction to go in. And that's what we call gradient descent. So we're trying to find the direction of the steepest slope downwards, and then take a small step by nudging the weight. So if you imagine you're at the top of a mountain, and you're blindfolded, and you've got to try and make your way to the bottom, you stick your foot out, and you feel around a little bit, and you try and feel where the biggest slope is, and then you just take a little step in that direction, and you keep doing that. And you don't want to take too big a step, because you might end up falling off a cliff. But you also don't want to take too small a step, because then it's going to take absolutely ages. And the same applies with gradient descent. So let's try and visualize it. So we'll start off with quite a high loss function. And at this point, the network is predicting that it's kind of roughly half-half chance that it's got a cat or a dog. And although it looks like the cat it says that the cat is actually slightly more likely to be a dog, and the dog is slightly more likely to be a cat, which is obviously wrong, so we want to try and fix that. So we do the gradient descent thing, take a small step down, and we see that the network predictions have improved slightly. Take another little step, and we see them improve again. And we just keep walking in the greatest direction of the slope. And as we go, the network predictions get better and better until we get right to the bottom, and it's saying that it's pretty much 100% chance that a cat is a cat and a dog is a dog. So we're happy. So we calculate the slope using differentiation. And we start at the output layer and we work backwards through the network. And that's what's called backpropagation. So if you've heard of the backpropagation algorithm, that's what that means. And then we nudge all the weights a little bit in the direction that we calculated. And the amount we nudge them is determined by the learning rate. And that amount is the equivalent of the little step down the mountain. So the learning rate is the size of the step you take down. OK, that was a bit much. But as I said, it's OK if you don't understand all that, because you can always read about it, but also because TensorFlow pretty much does it all for you. So if you want to do any of this in practice, you can use TensorFlow, or there are other libraries available. But TensorFlow is Google's open source Python machine learning library, and it's got lots of inbuilt functions that can deal with the tricky maths. So it takes care of things like gradient descent. And there's loads of good documentation and lots of tutorials, so it's quite easy to get started. OK, now we're going to move on to looking at convolutional neural networks, which are a slightly different version of what we've just talked about. So instead of treating each input as an independent value, so in what we've just been talking about, I've essentially been imagining that each input would be 1 pixel, the value of 1 pixel of the image. But if you think about an image, the pixels aren't completely unrelated to each other. If you take any random pixel in an image, chances are that it's going to have a relationship with its neighbors. It's probably going to be a similar color to its neighbors. And ConvNets take advantage of that structure in the input data and the 2D structure of images. So that's why ConvNets are great at image processing and computer vision tasks. So I was really pleased that Martin's talk covered this a little bit earlier, but just to remind you, images are 2D arrays of numbers. Well, grayscale ones are 2D anyway. So we have a nice picture of a 3, and I've pixelized it just to show you what I'm talking about. And if we zoom in, we can see that the white has got the highest value of 1, the black has a value of 0, and then the gray has a value of 0.8 in between. So all images are just arrays of numbers. So there's something called the convolution operation. And what this means is you take a smaller array of numbers, which is called a kernel filter, and you pass it over every pixel in your image. And you essentially, hopefully you can see from this diagram, you multiply up the values and then add them together and then put that in a new array. And that's a convolution operation. And we use these all the time without realizing it. Every time you use Photoshop or take a photo on your phone and put a filter on it, that's what's going on. It's one of these convolution filters. And depending on what effect you want to do, the numbers in that kernel filter will be different. So here we've got an image, and if we want to blur it, we choose a convolution filter, which essentially takes the average of all of the pixels' neighbors. And that just makes that kind of blurry look. If we want to sharpen it, we do the opposite. So we kind of really enhance the center pixel, and then we sort of de-weight the pixels around it so that it becomes much sharper. And then edge detection is just a much more extreme version of that with an 8 in the middle and then -1 around the edge. So just to go back to our original neuron, we had a whole load of inputs. We had a whole load of weights that were multiplied up. We add in our bias. We put them through an activation function, and then we output the result. Okay? With a convolutional neuron, the structure is very similar. But instead of having independent input values, we now have a whole set of arrays as our input values. And instead of multiplying them by lots of individual weights, we use a convolution operator, and we have a shared kernel filter. And the weights are actually the values within that kernel filter. We still have the bias, we still add them all up, we still put them through an activation function, and instead of outputting a single value, we now have an output array at the end. But if I just flick between them, it's pretty much the same structure. OK, so now let's talk about some of their applications. So there's something called the ImageNet challenge, which is what's used to test algorithms for object recognition. And so this is an example of some of the results. So you get a whole load of labeled training data of lots of different images with lots of different objects in them. And then people write algorithms to try and identify what those objects are. And you get results like this, which kind of give you a probability. And so you can see on the right-hand side, there's a leopard, and it's got quite a high probability of being a leopard, so that algorithm's doing well. And then it's got slightly less probabilities for some of the other animals. So until 2011, a good result in this challenge was a 25% error rate, so it was still getting a quarter of them wrong. But in 2012, ConvNets were introduced, and suddenly the error plummeted to just 15.3%, and that's a massive difference. Before, it was kind of like hovering around a 1 or 2% improvement, and then it suddenly jumped down like 10%, so that was like pretty amazing. And then in 2015, ConvNets actually outperformed humans, so it's getting pretty impressive. OK, so let's have a look inside of ConvNet. So as I said, images are just arrays of numbers, and the kernel filter is also an array of numbers, and that means that we can visualize what's going on inside the kernel filters. So in the early layers of a network, the kernel filters tend to take on these values which are, they kind of look like very basic shapes. They're lines, they're patches of color, they're kind of different orientations, but they're very sort of basic. The mid layers then start to have a bit more structure to them, so we can see things like corners, circles, the sorts of things that cobbled together would make up different objects. Then in the later layers, you can actually see much more clearly kind of properly defined objects. So you can make out things like a tire and I think like a window. And so it's combining up all the previous layers into something that's actually recognizable as an object. And again, this is very similar to how our human visual system works. And this has some pretty fun results. So a research team, Gattis et al., managed to realize that if you want to train a network to recognize a cat, for example, it should recognize that it's a cat, whether you give it a photo of a cat or a hand-drawn cartoon of a cat, for example. So it needs to understand the difference between the style of an image and the content of an image. And what they found was that a neural network was learning to abstract away this style information and ignore it so that it could focus on working out what was actually in the image. So some of the layers of the network were dedicated to content recognition, and some of the layers were dedicated to style. And what they found was they could take the style layers from one image and the content layers from another image and then kind of smush them together and then create these amazing works of art from photographs. So you just take a photograph and you can choose a painting, and suddenly it can make your painting in the style of that, make your photo in the style of that painting. I had quite a lot of fun with this in an app called Prisma. You can take a selfie and you can choose a work of art, and it will just make you look like you're a masterpiece. It's pretty fun. But they're also easily fooled. So there was a ConvNet that could identify correctly this truck, but then they realized that they could apply some imperceptible distortion to it, and then it would, for some reason, decide it was an ostrich. And it also decided that this was 100% goldfish. So you might have heard of Google's Deep Dream, and what they did was, using a trained ConvNet, they ran the process in reverse. So they actually told the network, whatever you detect, enhance it. So instead of nudging the weights of the network, they nudged the image. And then they repeated that over and over and over and over again. And so this is an example of a before and after. So you get a before picture, you say, what do you see in this image? And the network enhances what it sees, and then it kind of has these mysterious hallucinations of cars and buildings and things like that. Here's another example. And again, lots of buildings, lots of dogs. A lot more dogs. A lot more dogs. So you might be wondering, why are there so many dogs? And the answer to that is that the training data that they used was made up of common images, and a lot of common images like out there are dogs. So the network was biased to seeing dogs in these images. And that's what we call algorithmic bias. So it's important to remember that machines are neither infallible nor objective, and the network is actually just seeing what it's trained to see. And that's kind of dangerous because as humans, we are the ones choosing the training data, we are the ones designing the architecture of the network, and that means we can transfer our own biases. And yeah, Jenna's talk showed us a whole load of human biases we have, so we have to be a bit careful of that. Because networks can inadvertently learn proxies and correlations instead of real insight to the data. And then that can produce racist, sexist, and other irrational results. And actually, that sort of thing is getting a lot of coverage at the moment in the media. And it's kind of scary as this becomes more and more pervasive in our lives. But there are some things you can do to help. So first of all, try and understand unconscious bias. We all have it, and we're all going to accidentally put it into our programs. So it's much better to have an awareness of it than be completely oblivious. You can also test to see if the network has learned what you want it to learn using something called output testing. And it's also important to diversify your training data so you don't end up just with seeing dogs everywhere. And it's also important to diversify your engineering teams. The more people we have from lots of different backgrounds working on these problems, the less likely we are to run into some of these very narrow and biased systems. So there's a whole lot of stuff we haven't covered. But this guy, Andrej Karpathy, is like one of the top guys in ConvNets at the moment, and he tweeted, "Everything I know about the design of ConvNets is useless in real life. Super basic 4-layer ConvNets work best." And if you remember, we've seen how to make a convolutional neuron, and we've seen how to make a 4-layer convolutional network. And I've said you can just make these with TensorFlow. It's pretty straightforward. So you're sorted, basically. Thank you very much.